Hey there, chemistry team. It's your chemistry coach coming at you with video number 1 in a new chapter studying thermochemistry. And this is kind of a sub branch or tiny portion of a larger branch of chemistry called thermodynamics we'll be getting into later. So this is just kind of our warm up, specifically focused on one aspect of thermodynamics, the study of heat, right? So thermo, you think thermometer, thermos, those kinds of things. You think heat, all right? So what we're going to be looking, mostly at, hey, if we have a chemical reaction, is there a change in energy of that system, right? Is the system, we're focused on having energy here. Does it end here? Are we starting here? Does it end here? Does that energy, overall energy of the system being the portion of the universe we're studying at that point in time, right? Does that energy change, and how does that change? Heat is one way that can happen. We're going to look at it, qualitatively and quantitatively, how you can change the energy of the system through loss or gain of heat. So let's define. A lot of thermochemistry and thermodynamics is all about your frame of reference, how things are defined, terminology. So we're going to go through a lot of that to begin this first video. So first and foremost, we need to make sure we're all speaking, on the same page, right? We're at the same wavelength. So let's define portions of the universe that we're studying versus the rest we're not particularly interested in, okay? So let's take that portion of the universe that we're interested in at the time and call that our system. All right, so this is going to be our system right here. And as a chemist, our point of view is always from the point of the system. So I like to, imagine myself as that system, right? Like, okay, I've got some energy. Am I losing energy? Right? Is my energy going down? So if my energy is going down, that's going to be lost outside of the system. So we're going to call everything in the universe outside of that system, whether that system is a couple solutions poured together in a test tube, or a planet, or a kitty cat. Yay, BT kitty cat, right? So whatever you're focused on, that is your system, right? And then everything else in the universe is our surroundings. All right. Now, it can be a little weird to think about, yeah, I do a chemical reaction in my lab. How does that affect Pluto? Oh, come on. Usually we're just looking at the localized surroundings around your system. But it can be pretty weird. There's going to be some fun stuff. And this is the frame of reference is going to affect our signs. So what I found when I was a student in thermodynamics, in thermochemistry back many, many decades ago, I always got frustrated. I'm like, how come I'm off by a negative sign, man? I got the right number, but I got negative. The answer's positive. I was like, because my frame of reference was off. All right. So if we have the same frame of reference, we should end up with the same, right? Because the system could obviously lose energy or gain energy. Well, it could be the same if I have the same amount of energy going from the surroundings to the system versus system to surroundings. It's the same numerical value. It's just the sign's different. So this will be our frame of reference right here. So I'll just put reference point. Boom. So if you are the system and you're losing energy, your energy goes down. The system's energy goes down. That energy must go to the surroundings, and so the energy of the surroundings goes up, but the total amount stays constant. So that's going to be one of the laws of thermodynamics coming up. Woo-hoo! Right? So we've got our definitions, systems and surroundings. Let's identify. Let's just start with the big picture in this, and then we'll work down the little components of it. We're going to take a look at this system and go, hey, what is the total energy of that system, right? We're going to call that the internal energy. So I'll write that down. Internal energy. And we're going to call that U, right? I would have called that E or I or something, but no, most textbooks I've seen call that U, capital U, the internal energy. Why U? I don't know. So that contains all energy of the system, all of it. So think of that, maybe in a broader sense, all the potential and kinetic energy of that system. Okay? So let's go all potential and kinetic energy. And if you've taken physics, you're familiar with both of those terms, right? Or even some basic science, kinetic and potential energy. So potential energy, again, could be, due to chemical compositions, bonds and things like that. It could be position or placement. Kinetic energy, obviously, being energy of motions. That could be, vibrations. So you've got some atoms with some bonds and they're vibrating this way, right? Or maybe you've got molecules rotating or bonds rotating around themselves. Electron motion, translational motion of gas particles, right? All of that kind of motion gets wrapped up in the kinetic energy aspect of it. So if we take all that, wrap it up, we'll call that internal energy. And what we're interested in is changes in internal energy and how we can theoretically or experimentally measure that for the system. All right. So if this is going to change in energy, how can that happen? That's ultimately where we're after. The units for this is going, well, depending if you're, been around the block a few times, you're probably familiar with calories. But if you're looking at the the IUPAC, International Union of Pure and Applied Chemistry, they like the units of joules for that. So let's do that. So energy units. So you've got the calorie, which is CAL, or the joule, which is capital J. All right, so you can find, conversions factors for that. I think it's 4.184 joules per calorie, if I recall. You can find those in any textbook or table or anything like that. So calories kind of an older system of energy units that's still used quite a bit by people, whereas joules is where, people are trying to, at least scientists in chemistry are trying to become more consistent in using those kind of IUPAC units. And that's a conglomeration of kilograms, meters squared per second square. It's got a lot of weird units combined in there. So what I'm going to do is I'm going to drop another board, and let's look at different types of systems we can look at and control in the laboratory. And then let's look at ways we can change that energy and how that can be measured. Be right back. All right, gang, let's have a look at, and you'll hear these terms when you read through textbooks and go through labs and those kinds of things. And what you set up in lab, you have to understand, what kind of system have I set up? What kind of interaction can that system have with its external surroundings, right? Are we sealing it off from the surroundings? Are we opening it up to the surroundings? So three different, so we got two extremes and one that's kind of in the middle. So the first one, and one of the most common ones that's used, in a laboratory, take a test tube of one solution, maybe a strong acid, test tube of another solution, maybe strong base, mix them together. Oh, it gets so warm. Mix it up real good. That's open to the atmosphere. It's glass, so heat can flow in and out. It's completely open. There's no restrictions between the system and the surrounding, right? So what we do is, if we have a situation like that, we call it an open system. Heat is allowed to flow, right? Or we'll think of it as energy in this case. We'll get to heat specifically in a little bit. Let's look at energy in general. So energy is allowed to flow in and out of the system, right? So energy can go in and out of the system. Totally, completely open to it. And let's do the fact that it's open, so we could have, let's say we generated a gas. That gas could flow out and dissipate in the environment, right? Maybe we created some water vapor or something that can trickle out. So it's open to matter as well. So you can have energy going in and out, and you could have matter also going in and out. Commonly, that energy will be through heat, but we'll find out work is also a part of that, right? Ways that the system can lose or gain energy. Now let's take a situation and say, well, let's say I'm okay with energy, possibly through heat or whatever going in and out of the system, but I want to contain any gases. I don't want gas flowing in and out, something like that. So I want to trap the matter. Yeah, just stick a cork in it, tell my kids, put a cork in it. In that scenario, energy could still flow in and out, right? So I could still have energy flowing in and out of the system. So if I had, say an exothermic reaction, it would feel warm. to my hands. I could feel the heat leaving the system going to the surroundings because I'd be part of the surroundings, right? But it would trap matter. This is sealed off, right? So matter cannot go in and out. So I'm going to put a big X through there. So no matter. Let's put no matter exchange. I was going to leave it as no matter, but that could mean something else. And no matter. But there's no matter exchange, obviously, because it's sealed off from the surroundings. And in several situations, we'll see what like calorimeters are later or something like that. What if I don't want energy to flow in between the systems and surroundings or matter? Right, so you pour yourself. When I get up, I have a long commute. I'm on the road 2 to 3 hours a day. So if I'm on the road at 5:30 in the morning, I got to drive for an hour and a half, 2 hours. I've got my morning tea, right? But my morning tea, I'm kind of silly. I understand the stuff, but I like the feel of a mug, an open mug, right, with my tea bag in it. So I'll nurse that. But I'll tell you, after half an hour, 45 minutes, my tea is not so hot anymore. So I'm drinking cold tea, right? So because it's losing heat, right? Heat's flowing between the system surroundings. A lot of you people who are smarter than I am, you'll be like, I'd like to keep my tea nice and warm for my morning commute. So what you do is you put it in a thermos, right? So you have something like a thermos. And that is sealed off, right? So matter can't flow in and out. There's no matter exchange. So we have no matter exchange between the system and the surroundings. If I could spell, this would be better. So no matter exchange. And no energy exchange. Energy is not going to be flowing in and out of the system if you had like a perfect thermos. I got the perfect thermos. It stays the same temperature the whole time. So we have no energy exchange either. So I'll put a big X through that. No energy exchange. All right, so pretty simple definitions, but every once in a while we're running into an isolated system, and that changes our way of thinking a little bit. It gets a little weird because it prevents flow between the system and surroundings. So let's look at the changes in internal energy and how that can occur. All right, let's take a look at change. We're very much interested in changes in thermochemistry and thermodynamics, right? It was a lot of chemistry, actually. Initial pressure, final pressure, in a burette. Initial volume, final volume. Temperature changes. Initial temperature, final temperature. Same thing's true with internal energy. Let's say I have a system at some defined state 1, some defined temperature, defined pressure, etc., etc. And it's going to have some internal energy. Let's call that U1 for state 1 or U sub I for initial. We're at the initial state 1, right? And some kind of change occurs, right? And we rise it up to some new value, right? Some new defined pressure, defined temperature, right? So all of this, the parameters of that are defined. That is a specific value. And what's really neat about this is internal energy is something called a state function. U is a state function. So what does a state function mean? It means it's path independent. It doesn't matter how it got there, right? I could have got here, directly. I could have gone here, then here, then here, then here, and here, to here, to here, here. So it doesn't matter how many steps it took to get there. These initial and final states are defined, right? They're not going to change. So no matter how I get there, the difference in energy between them is going to be the same, right? Because that'll never change. It doesn't matter. So that's called a state function or path independent. Path independent. You'll see these terms path dependent and path independent, but it's a state function. So a lot of thermodynamic parameters are path independent. Doesn't matter how you get there. Now, it turns out measuring the internal energy at a specific state, not going to happen. So there's no way we're going to know the specific U value or the absolute value for the internal energy in state 1 or for state 2. Not going to be measurable in a laboratory. But we can measure the difference between them, which is the change in internal energy, right? Which is the final minus the initial state. Right, so getting from here to here, that can be measured. I'm going to write that down. So I'm not going to be able to measure the final, not going to be measure the initial, but I can go in the lab and measure the change in that. So what we're really interested in is how can I get that, right? What allows me to interchange energy between the system and the surroundings? And that's going to be our heat and our work, which is going to be pretty important a little bit. It turns out heat and work are not state functions. They are path dependent. Depends how you do it. So let's put another system on the board and look at how we can lose or gain energy from it. All right, gang. So we've got a system with some internal energy, right? We've got internal energy. All the potential, all the kinetic energy that's in there. If that's going to change internal energy from one state to another, only two ways we can do that. All right, so two ways we can change it based on heat flow between the system and surroundings, or work being done or performed between the system and surroundings. So you probably learned these definitions before. I throw up some simple ones. Heat, of course, is an energy transfer due to temperature differences, right? So, you snuggle up with someone who's, so I always think of myself, I'm an exothermic, person. I'm always hot. I'm like, oh, I don't want the sheets. I want the window open. I'm so hot. And some people are more, oh, my hands are always cold. Blah, blah, blah. It's a perfect fit, by the way, right? So if I snuggle up with my wife or something and she's, cold or whatever, she's a lower temperature. I'm a high temperature. Oh, heat's going to flow. Well, heat doesn't flow, just energy flows, changes. I lose energy. She gains energy through the transfer of heat. You don't contain heat. I can't say I have a lot of heat, right? Heat is an energy transfer, right? That's a way to transfer or change energy. Based on the temperature differences, always from high to low. And again, temperature is just a measure of atomic and molecular motion. You got vibrations of atoms, so a low temperature, they're moving slow. You increase the temperature higher and higher and higher. You got this increased, molecular or atomic motion that's reflected by temperature. The higher temperature, the more motion you have. All right. Work, of course, especially for my physics people. Shout out to you, Price Man. I know you're watching. I know you love physics. And I'm simplifying this from a chemistry perspective. Force acting over a distance. So if I want to bicep curl this pen, right? The gyms are closed down, so this is hard now. I'm lifting up this weight against gravity. There's a lot of equations for that. But anyway, chemists tend to focus more on the heat, right? We deal with work. We'll talk about work in a little bit, usually due to gas expansion or contraction. That's typically how a chemist looks at work. But let's take a look at the system surroundings interaction. So here's our surroundings. And if I want to change the internal energy of that system, I can do that through transfer of heat. Okay, so if heat is coming out, right, and heat's going to be Q. I called it H, but it's Q, and work W. That makes sense right there. So if heat is flowing from the system to the surrounding, it's losing energy through heat. All right, that means the energy of the system's going down. Everybody agree? So from the point of view of the system, its energy is decreasing. That would be a negative Q going from the systems to the surroundings. Right? And in lab, we would call that like an exothermic process because we're the surroundings. We feel the heat coming from the system, feeling hot. Now, in the other way around, if heat is going, if the energy is going from the surroundings to the system and the heat is going in the other direction, we would call that a positive Q, right? So if we've got energy going into the system via heat, the energy of the system is going up. It was here, heat went in, boop, up it goes. So that's positive from the system's point of view. Oh, I'm the system. My energy just went up because heat came in. Doesn't matter what from. And in a like way, look at work. if the system does work on the surroundings, right? Usually like a gas is created and expands against the surrounding atmosphere, right? It's doing work on the system, pushing against it. Well, the system's losing energy because it's pushing against the surrounding atmosphere. So in that scenario, if the system's doing work on the surroundings, got to have a negative sign there. It's all about the negative and positive signs. I mentioned that earlier, right? So where's the negative sign go? What equations? Thermochemistry, thermodynamics. What equation do I use? And is it positive, or is my thing going to be positive or negative? Right? So from the system's point of view, if it's doing work on the surroundings, the system's losing energy. The surroundings is gaining energy. So from the system's point of view, work will be negative. If heat's going from the system to surroundings, the energy of the system's dropping, the energy of the surroundings is increasing, but since the system's dropping, that's a negative Q. Vice versa, if we do it in blue, boom. If he's going from the surroundings into the system, it's positive Q, and if the surroundings are doing work on the system, energy is going to the system, so the energy of the surroundings is going down, energy of the system is going up. That would be a positive W, all right? And this is all wrapped up in one beautiful equation called the first law of thermodynamics, or the law of conservation of energy, all right? So let me erase this real quick, and let's write this down, the first law of thermodynamics. You know what? I'm going to pause it. This deserves its own board. All right, let's polish off this introductory part on systems and surroundings and internal energy, heat and work. All right, first law of thermodynamics. There's going to be three big ones we're going to be looking at. All right, this is the first law of thermodynamics, is the law of conservation of energy. And hopefully this makes kind of just gut level sense, right? If we've got energy flow between the system and the surroundings, right? So let's say the system loses X amount of energy. It's got to go somewhere, right? It goes to the surroundings. So the system would be losing X amount, which means the surroundings would be gaining X amount. It's the same number, correct? But one is positive. So in this case, it'd be negative X for the system because it's losing it, positive X for the surroundings because it's heading that direction. So the surroundings goes, oh, I'm gaining energy. The system, I'm losing energy. Same value, though. You can't destroy energy or create energy out of nowhere. It can just be transformed from one form of energy to another. So the total energy is constant, and energy cannot be created or destroyed. How does that work into a quantitative equation for us? There's two ways you can think about it. Right? So now remember, if I've got a system at state 1 and a system at state 2, this has got its internal energy at state 1, internal energy at state 2, and so that would be the change in internal energy. Well, what's the only way we can change the energy? Work done on the surroundings or on the system, or heat loss to the surroundings or to the system, depending, right? So delta U can only occur based on heat flow and work being done. Remember, this is a state function. These are not. So if you take the total heat exchange between the system and surroundings and any work performed between the system and surroundings, add those together, that has to be the change in internal energy. There's no other way around that, all right? Commonly, there'll be no work done. We'll see how that works out later. If it's just dealing with heat, sometimes you'll see this also written as the heat lost by the surroundings or the system, it doesn't matter. So let's say the system loses some heat. Let's say no work's being done. That must be equal to the heat gained by the surroundings, right? It's got to be equal. You will commonly see the first law of thermodynamics expressed mathematically in one of these two ways, right? If both heat and work are happening, the total of the heat and work exchanges between the system and surroundings must be delta U, right? So if I know this and this, I can solve for that. If I know that and I know work, I can solve for heat. It's just three variables there. Or if there's no work being done, right, and only heat flow is allowed, then the heat lost by the system must be the heat gained by the surroundings. And you can put the negative sign on either side. It doesn't really matter. But those numbers must be equal to each other. You should differ by a sign. Welcome to thermodynamics. Right? So you can look at this, for example, let's say we had this much work done, and let's say we had this much heat done. You see that? So the total delta U doesn't change. That's why it's a state function. It's path independent. But I can change so I can make it all work or all heat. I could make it 90% heat, 10% work. So those can change. Those are path dependent. But it's just the sum of those two. So important equations there to write down. We'll look at specifically, we'll do a video just on work and a video just on heat, actually several videos on heat. This is thermochemistry, by the way. But this is a good little introduction on terminology for you guys. Enjoy.